So, okay. So, welcome you all to this problem solving session for the NPTEL course titled Multirate Digital Signal Processing. So, we are in fifth week for the course now. So today uh, I am going to discuss few problems with you, which are based on the lectures for the fifth week. For those who are attending this for the first time, this session, myself, Saurashis Chatterjee. I am a PhD scholar from IIT Kanpur. So let's start. So let me first write down the outline of the lectures in week 5. Week 5 lectures mostly deals with application of multirate signal processing. Second is spectral analysis of synthesis filter bank. Third, DFT and high resolution spectral analysis. And fourth one, trans multiplexer and maximally decimated filter banks. The fourth topic has just been introduced in the lectures covering week 5, so there will be no problems based on this one. Today's assignment problems mainly focused on first 3 topics. To be more specific, we'll look into different practical problems based on the spectral analysis of synthesis filter banks and DFT matrix to some extent. So let us move to first question for today. So here we can see, as we mentioned, spectral analysis for synthesis filter bank. So what does exactly mean? You can see this is a sequence x0 of n is fed to a upsampler block. This we have encountered in previous sessions, so we are pretty familiar with that. Next is it passes through this filter with response f0 z. Then you can see a second sequence x1 of n, again passing through a upsampler block with upsampling factor of 3, and it passes through another filter f1 of z, which is different from previous one, of course. And the third sequence x2n similarly passes through this upsampling block and the third filter f2z. And you can see these outputs are being added up to get a new sequence yn. So basically what's happening in a crude sense, at high level, if you see, different input sequences after various processing that include maybe upsampling, filtering, etc., are combined or to obtain new sequence. So why are we calling it exactly synthesis filter banks? Because their role is to combine different input sequences to synthesize a new sequence yn. This is precisely the reason we are calling it synthesis filter banks. Okay, let us move to the problem. Let me write down the intermediate sequences, the notations mainly. After upsampling, it's x naught dash of n. This one similarly x1 dash of n. This is x2 dash of n. Here we obtain x0 double dash, x1 double dash of n, and x2 double dash of n. These intermediate sequences we use because it helps us to break down the entire problems, this large problem, into simpler modules so that we can correctly interpret their impact to obtain this final output sequence. By the way, you can see these filters f0, f1, f2 are nothing but ideal brick wall uniform synthesis filters of double-sided bandwidth 2 pi by 3. Centered, of course, their centering frequency are different, and we are interested in the spectrum of y of n. So these are 4 options: option A, option B, option C, and option D. So let us introduce a new slide to discuss our problem in greater details. I think we may need 2 slides, so we are adding them. Okay, first we write down the necessary data for us. F naught to the power j omega centered around omega is equal to 4 pi over 3 f1 centered around omega 2 pi over 3 and f2 around omega 0. So let us draw their responses for better understanding. Let us denote them with different color. First we draw f2 of e to the power j omega. Center frequency 0, have a double-sided bandwidth. Let me write here double double-sided bandwidth is equal to 2 pi over 3. So this is minus pi by 3, this is pi by 3. Let us denote this one as 2 pi over 3 and this one as 4 pi over 3. These are center frequencies. So let us use some different color first, then I will explain. Okay. So you can say this is pi, this is 5 pi by 3. Yep. So yep. So this one is f naught, spectrum of f naught. This one is spectrum response of f1 and this one is of f2. See, f2 is centered around 0, f1 centered around 2 pi by 3, f0 centered around 4 pi by 3. Now you see, according to the question, they are ideal brick wall filter. So although their edges are at the same omega, they are not overlapping. They are placed side by side, of course without any gap, which is not practical very much, but in ideal sense this is a brick wall filter, such that this for consider f2 abruptly ends on pi by 3 and f1 just you move slightly right of pi by 3 if the f1 has a magnitude response. So these are ideal brick wall filter. In practice you won't get such abrupt cutoff frequency behavior. You have a more something like this, but that is not our concern as of now, so we'll let it go. So let us see the response of x0 n x0 of j omega. So you can see that x0, x1 and x2 are all the frequency responses spans from minus pi to pi. So let us denote them. this is x naught of e to the power j omega. Center frequency 0, spans from minus pi to pi. Now when you pass this through a upsampler block of upsampling factor 3, you obtain x naught of n, whose corresponding frequency spectrum is denoted as x naught dash of e to the power j omega. So what do you obtain in the output? The frequency spectrum of x naught dash of n. Now you can see if you pass a signal through a upsampler block, the frequency domain spectrum contracts basically. What does it mean? Two things happen. First is contraction of frequency, that is earlier your edges are at minus pi and pi. Now in the new frequency axis they contracts to minus pi by 3 to pi by 3. But not only that, upsampling, let me write it down. We have seen this point in previous problem solving sessions, but no harm in reiterating it again and again because it's a very important property. Upsampling by factor of L introduces L minus 1 additional copies of original spectrum. So what do we get? Here it is upsampling by a factor of 3, so we get 2 more copies centered around respectively at 2 pi by 3 and 4 pi by 3. This is the spectrum of x naught dash. Similarly, let us write down the spectrum of x1 and x2 of n also in different color to make things clear. X1 is trapezium shaped, so let us draw it. Actually it's symmetric, but because of my drawing it looks unsymmetric, so please ignore that. By the way, this keeps repeating every 2 pi interval. I didn't shown that. I am only concerned about this minus pi by 2 to 2 pi axis, 0 to 2 pi or minus pi by 2 axis. But for any discrete spectrum, for spectrum of discrete signal, it is repetitive in nature only. So although we are not explicitly mentioning it here, we should always keep these things in mind. So similarly here also, your bandwidth contracted, so does your frequency edges, spectrum edges, and introduction of 2 additional copies at 2 pi over 3 and 4 pi over 3. Similarly for x2 n, the input sequence whose spectrum is triangular in nature, now for your better visualization, let me write it here. X naught dash of n passes through this filter f naught of z x1 dash passes through filter f1 of z, and x2 dash of n passes through f2 of z. Where f naught corresponds to this one, f1 is this one, and f2 is this one. So when x naught of n, whose spectrum is given by this one, passes through f naught of z, you see f naught of z is okay. Let me write it down in the next page. Okay, copying is not happening, so I need to manually write it down. Okay, let me write it down. F naught of to power j omega, its expression. It is centered at 4 pi by 3 brick wall filter, and x naught dash n passes through it, whose frequency response is as follows. So time domain convolution results in multiplication in frequency domain, which means this f naught of j omega only allows the portion, let me write it down here, of x naught dash between pi to 5 pi by 3. So you can see that when you pass this sequence x naught dash fin through this filter with the frequency response f naught of z, it only allows this portion of input spectrum to pass and discards the rest of the spectrum. So what we obtain here? This is f naught of a to the power j omega times x naught of dash of a to the power j omega, which is this part. Let me write it down for other filters also. Sorry for the interruption. There was some malfunction in the voice. If one of z is centered around pi by 3, sorry, 2 pi by 3, and when you pass x2 dash of n through it, sorry, x1 dash of n whose frequency response is x1 dash of e to the power j omega, whose visual representation is something like this. Please ignore this overlap. Actually, there should not be an overlap. This is a drawing mistake. Zero, 2 pi by 3, 4 pi by 3, pi by 3. So when you pass x1 dash of n through this filter f1, it is only interested, as shown in the previous example, in this part of spectrum and discard the rest. So you obtain something like this. And the last one, which is f2 of e to the power j omega, whose spectrum is centered around angular frequency omega is equal to 0. When you pass the sequence x2 dash of n through it, it will only allow this part of input spectrum to pass. Resulting output spectrum is given as okay. This is f2 times e to the power j omega times x2 dash e to the power j omega. Now this is continued to continue to previous slide. I don't want to introduce another slide because then things would be too messy to follow. Okay, I guess I need to introduce that. Okay, from the figure you can show yn is given as the summation of x naught double dash n plus x1 double dash n plus x2 double dash n. If you take the transform on both sides, it turns out to be x naught double dash e to the power j omega double dash e to the power j omega x2 double dash e to the power j omega. Now x naught or double dash e to the j omega is nothing but x naught dash of e to the power j omega times f naught of e to the power j omega. Similarly, for other two sequence, we can write this. Now you can see this is basically summation of these three spectrum that we have already calculated, and you can see that these three are non-overlapping. See, this one is centered around 0, ends at pi by 3. It starts from pi by 3 and centered around 2 pi by 3. Then it's centered around 4 pi by 3 and starts from pi. So these three are overlapping. So if we sum them up, we get this. The spectrum of y to the power j omega we get as follows. So this is the spectrum of the output sequence yn. So let us see which of the option matches with our answer. Yes, I think this one does. From minus pi by 2, 3 pi by 3, this one, this spectrum triangular, then around 2 pi by 3 you get the trapezium shaped spectrum, and then around 4 pi by 3 get. By the way, if you see that this is nothing but a fundamental behavior of spectrum at discrete domain signal. It is because these things, this whatever is 0 gets repeating at every 2 pi interval. That is the only reason. That's what. So the answer is A. correct answer. So let us move to this question. When you have this sequence xn which has been at the first branch, you direct fed, you are feeding the input sequence xn in its own original format to a downsampler block. The downsampling factor you are feeding it to a downsampler block with a downsampling factor of 3. Then you pass xn through this block. Z is nothing but a advanced block, fundamental discrete signal processing block. That is, you obtain x n plus 1 here. You fed this advanced version of your input sequence to the downsampler block in the second branch. Then you pass to another advanced operator and you get xn plus 2, and you fed this advanced version of xn, which is advanced by 2 units, to this downsampler block to get yn. So the question is, what is yn? What should be your output sequence? So let us write down the expression of xn here. Which is denoted as, this box by the way denotes the position of 0th index. Now we need to find x n plus 2. Advanced operation basically means shifting the sequence to left by 2 unit here, of course, because the advanced. Okay. There should be 7 here missing. So now the position of 0th index shifted here at 3. And now you perform the downsampling operation, that is y of n, which is nothing but x 3n plus 2, which you can obtain let us denote which one we are going to keep and which one samples are going to discard. Downsampling by a factor of 3, as we have seen in lectures and previous problem solving sessions multiple times, that basically downsample by factor of L leads to keeping only one out of L samples and discarding the rest. And which one you are going to keep? Keep samples whose index are multiples of L. So 0th index you are going to keep. You are cancelling out 4 and 5 because they respectively denote the first and second index. Oh, sorry, there should be change of color here, better representation. This correspond to first and second index, and then you keep 6 because this corresponds to third index. You again ignore 7 and 8 because this correspond to fourth and fifth index, which are not multiples of 3. You pick 9, this is the sixth index, and you ignore this is -1 and -2 at index, which are not again multiples of 3. So we are going to ignore this. So here we are going to obtain 3, 6 and 9. It is the position denotes the 0th index, the arrow denotes 0th index. Therefore you obtain yn as 3, 6, 9, which is the third option. Okay, let us move to question number 3 here. So here you can see your sequence, input sequence xn, which is denoted as like this. Input sequence xn is at first branch fed to a downsampler block with a factor 2 in its original format. Then is passes through a delay block by 1 unit and fed to another downsampler block. Then it is fed again to a 1 unit relay block and fed to a downsampler block here to obtain output yn. We are interested in what is the sequence yn, output sequence. So you can see when you pass xn through this z inverse block, you basically delaying the sequence, input sequence by 1 unit. You pass it again through another delay block, you are getting xn minus 2 here. So ultimately it turns out we are feeding xn minus 2 to this downsampler block to obtain this output y. Basically yn is x to n minus 2. So first write down xn again. This denote the 0th index. Now let us down the shifted version of n minus xn minus 2. Delay by 2 units corresponds to moving the sequence on right hand side. Now this 0 become the 0th index. Since you are shifting the whole sequence right by 2, you have to introduce 2 0 value samples here. So next, if we are interested in downsampling the above sequence by 2, Basically we are going to keep even number of samples and discarding odd number of samples. So let us pick the even number of samples first. This is a 0th sample, this is 2nd, this is 4th, this is 6th, this is 8th, this is 9th, and we are going to discard these odd indexed samples. To obtain x2 n minus 2, this modified, this shifted and downsampled sequence as follows. Which is the sequence yn. We obtain the output of this third branch. Therefore we can see the question. Third option is the correct one for question 3. Here you can see, let me write down the problem here again. You have input sequence x0 n, you are feeding it to a upsampler block, then passing it through a advanced operator. You have another sequence x1 of n, pass it through upsampler block, adding it up with the output of previous on the branch above it. The third sequence x2 of n, passing through a upsampler block and adding up to the output of two branches above to obtain sequence yn. So you can see we have three different input sequences. We are passing them through this upsampler block, and delays, we have to introduce a delay here. Let me correct myself. Okay, yeah, fine. So what I'm saying that we have three different input sequences. We are passing them through different filtering processes, like we are passing them through upsampler block and advanced operators to obtain a new signal yn. So basically you are synthesizing this sequence yn from by combining different input sequences given as x0, x1 and x2. So this is a synthesis filter bank. So if you are careful here, you can see in this question you are given the input sequence x0 of n and x2 of n and the output yn, and you are asked about the unknown sequence x1 of n. So let us denote x1 of n as some unknown values. Let's denote them as e, f and g. Let's assume these values are unknown. we need to find their values. We'll see how these assumptions will later simplify our job of finding the sequence x1 of n. So let us denote this intermediate sequence as x0 dash of n. This one is x1 dash of n. As we have seen from earlier problems also, defining this intermediate sequence is going to help me break down the entire problem into submodules and simplify the analysis, and also great intuitive understanding of what's happening underlying, although they are not readily necessary. Or okay, and this one is x2 dash of n. Okay, so this one after passing through a advanced block becomes x naught of dash of n plus 1. So the sequence here becomes x1 dash of n plus x naught dash of n plus 1. After passing through another unit of advanced operator, we obtain here x1 dash of n plus 1 plus x naught dash of n plus 2, and we already have x2 dash of n here, so we obtain yn as x naught dash of n plus 2 plus x1 dash of n plus 1 plus x2 dash of n. Okay, please excuse me for 2 minutes here. Okay, so let us first consider the input sequences whose values are given to us. So x naught dash of n is equal to x naught of 3n, sorry, x naught of n by 3, sorry, x naught of n by 3. So this basically means x naught dash can be obtained by introducing 3 minus 1 2 zeros between every sample pair of x naught of n. So that is upsampling for you. If you upsample a sequence by a factor of L, you are basically going to introduce L minus 1 additional zeros between every two samples of the original sequence. So if x naught of n is given as this, then x naught dash of n is going to be nothing but 1, 2 zeros, then 2, then again 2 zeros, then 3. And when you advance this sequence by 2, that means you are moving the sequence to the left, to obtain this sequence. Now we consider x2 is given, so x2 of n is given as 7 7 2, where x2 dash of n is given as 2 zeros, again 2 zeros, 2. And the sequence yn is given as 1 5 7 2 8 7 3 4 2. Let us denote this as equation 1, this is equation 2, this one equation 3, and this one equation 4. So let us first denote, if I subtract x2 dash from y1, what we are going to get? Let us see. Yn minus x2 dash n. We obtain, we see there's 1 and 5 going to be there, 7 is gone, then we have 2 8, then again this is 0, then again 3 4 10, then again 0. Now according to the question 1, this is equal to, let us denote it as equation 5. Now consider, now subtract x not of n plus 2 also. Let us see what happens. So from 5 you subtract 2, you see this 1 is gone, 5 is written, 0 is here same, this 2 is gone, 8 is written, okay, let us specify the position of 0 here. Okay, fine. Zero is there, then 3 is gone, 4 is written. Okay. So according to the question, this should be x1 dash of n plus 1 with the position of 0 here. This is given as 0 5 0 0 8 0 0 4 0. Now let us introduce a slide here, otherwise things are getting messy. Okay, the slide is entered at wrong position. Okay, this is fine now. So let us denote as equation 6, and let us write it down here again. x1 dash of n plus 1 is equal to given as 0, 5. 0 0. This is the position of 0 0 5 0 0 8 8 0 0 4 0. So your x1 dash of n should be I guess here I made some error. Let me check it. Okay, now I have done things correct only. I got confused in the index here. Sorry about that. So you obtain x1 dash of n from x1 dash from 1 by delaying delay by 1 unit, which correspond to shift of this zeroth index to the left. That is like this only. Now you obtain x1 of n. You perform upsampling on x1 of n to obtain x1 dash of n. So if you are interested in obtaining x1 of n, it is nothing but x1 of n over 3. So you are going to keep the samples whose index are multiples of 3 and discard rest of them. So let us see which one are the lucky samples. 0 is always going to be there, multiple of 3. 8 is going to be there. First and second index corresponding samples are removed. 8 in third index, fourth, fifth again removed. 6 is we are going to keep it. So the other indexes are removed. So what you obtain as this sequence 5 8 4. You can see it from this point of view also. If you remember, we have defined x1 of n to be E, F and G. Now x1 of n dash should be this. Now if you compare this with this, you could have clearly seen that And if you shift, of course, if you shift x1 dash n plus 1, it would be like this. In that case, it would correspond to this. So from both this way, you can see that E is 5, F is 8, and G is given by 4. So therefore your sequence x1 of n, you can approach the problem in both ways, is this. Let us see which of the answers which of the option matches with the correct answer. Often it's option B. So let us move to similar kind of question only. Only thing is that now instead of now the input sequence x2 is missing, x0, x1 are given, and y1 also given. So let us write it down. x0 of n, when passes through this upsampler block, we obtain x0 dash. It passes through a delay block, we obtain x0 dash of n minus 1. We see it becomes x1 dash of n after passing through upsampler. So therefore we obtain a summation here, x0 dash n minus 1 plus x1 dash of n after passing through another delay block becomes x0 dash n minus 2 plus x1 dash n minus 1. So therefore your yn, first let us write down. The expression is given as x0 dash n minus 2 plus x1 dash n minus 1 plus x2 dash n. We'll approach this problem in a slightly different way compared to the previous one. Let us see x0 of n first. It is given by 7, 7, 2, the 0th index. Therefore x0 of dash of n is obtained by introducing 2 zeros between every adjacent samples. And x0 of n minus 2 is obtained by shifting the sequence to the right. Similarly, for x1 of n, we have 5, 8, and 4. We make x1 dash of n as 5, 0, 0, 8. Zero, 0, 4, and x1 dash of n minus 1. You shift the sequence to right by 1 unit to obtain the following sequence. Okay, we obtain these two input sequences we need. Now we need x2n, let us denote as previously as E, F and G. Zeroth index symbol be E, and x2 dash of n is going to be E. This. So this is equation 1, this is 2, this is 3, this is 4. So if we add those up, this 1, sorry, 2, 3 and 4, that is x naught dash of n minus 2 plus x1 dash of n minus 1 plus x2 dash of n. We obtain this following sequence. You see the zeroth index, this is contributing 0, this is 5, this is E, so therefore it is going to be 5 plus E, comma, the second one contributing 5, 0 here, 0 here, so it's going to be 5 only. Oh, sorry, I was confusing between these two. Let me clarify it again. Okay, so this is contributing E, this is contributing 0, this is contributing 0, so it should be E here. The next is contributing 5, the next one contributing third index, second index contributing 7, fourth one is contributing F, fifth one is contributing 8, 0 here, 0 here, so 8 here. Sixth one is contributing 5th index is going to contribute here 0, 7 and 0. Sixth index is going to contribute 0, 0, G. Zero, 1, 2, 3, 4, 5, 6. Seventh index is going to contribute 0 here, 4 here, 0 here, so 4, and 8th index is going to contribute 2, 0 and 0. Okay. Now this I denote as V. Now if you compare yn expression, yn is equal to 1, 5, 7, 2, 8, 7, 3, 4, 2, and E 5, 7, F 8, 7, G 4, 2, we obtain E is equal to 1, F is equal to 2, G is equal to 3. Therefore we obtain the sequence x2 of n, our original input sequence, that you pass through these subsampler blocks and different delay blocks to synthesize a new sequence. You obtain x2 of n as 1, 2, 3 with 0th index at symbol value 1. So it should be answer B. Okay, so let us move to this question. It asks basically which of the following corresponds to impulse response which is not purely real. So let us write down the following fundamental property. What happens if Hn is real? Hn real corresponds to h to the power j omega being conjugate symmetric. And how we exactly reach this conclusion? Because real corresponds to h of n being equal to conjugate of n, that means h to the power j omega, that you write as this h of n to the power minus j omega n. You can also write this and you can also thereby write this because e to the power j omega n conjugate is e to the power minus j omega n. So this corresponds to h to the power minus j omega. This is conjugate symmetric property. Now how does this going to help us here? So visual let me write it down properly. Visual representation of conjugate symmetry is frequency response visual representation of conjugate symmetry is as follows, that your frequency response must be symmetric around the vertical axis. Basically, on both sides of this vertical axis, the spectrum response should be spectrum on both sides, negative and positive angular frequency spectrum on both sides positive frequency should be mirror image of one another. Now you can see this is mirror image of one another. This is fine. This one you can also see is mirror image of one another. This point maps to this point. This point is mapping to this point. I'm sorry, it's not like it is not correct. It is correct only. I'm just showing these points and these points mapping here, and these points mirror image of each other. The entire structure is mirror image to each other on both sides of this axis at positive and negative frequency domain. Let us move to this one. Okay, but this one is actually failing. These things is not mapping to this. If it has to be mapping, it should be like this only. If symmetric, it should be like this, but it is not, because this point is getting mapped here, which is not correct at all. This point should have been mapped here. If Hn to be real, and correspondingly its frequency response to be symmetric, it should be mapped here, but it's not. So therefore these are not symmetric. I guess we have found our answer, but still we'll move to fourth option. You can see it's rectangle only, so it's symmetric. Symmetric. Or we can write mirror image also. Mirror image. You can write for this also, mirror image. This one is also mirror image of one another, but this one is not mirror image. So therefore option C is the correct, that in the corresponding impulse response of this frequency spectrum, that time domain representation is not purely real, because if had it been real, the frequency responses are on positive and negative frequency domain should be mirror image of each other, or in other words, they should be symmetric along across the vertical axis. Okay, now let us move to the DFT representation. Here you have seen this is a sequence xn and different shifted version of xn's, basically m shifted versions, where this is xn plus m minus 1 corresponding to the delayed version of xn by m minus 1 unit. So this sequence is fed to this DFT matrix, which is of course a m cross m square matrix, which has many properties, whose columns are orthogonal, that fulfills the criteria of being an orthogonal matrix. By the way, it is also a unitary matrix also. So you can see this as at input you have m cross 1 vector. You are performing some matrix transformation over it. using a m cross m matrix, and your output is also a m cross 1 vector, but it's a transform vector. So at first branch we are going to get x naught of n, second branch x1 naught of n, at mth branch m minus 1 n naught of n. So we are mainly interested in the representation of hk of z, which is the response of x z x of z. By the way, the z transform of xn is given as x, sorry, let me clearly write it down. This is x of z, and x1 of n, the output at the first branch, and the first output branch is xk of n, which is the output of the kth branch. The z transform, if we take, it is xk of z. So we are mainly interested in the hk of z, the relation between hk of z and h0 of z, where hk of z is the transfer function for kth branch. So you obtain the DFT formula, if we remember. By the way, we can denote this xn as s naught of n, xn plus 1. Here the output is xn plus 1 advanced operator, s1 of n. Similarly, here we are getting xn plus m minus 1, which we denote as s m minus 1 of n. So basically, if we remember from the lectures, s of I n is equal to x of n plus I. And here I would like to write the z transform also, which is s z. From basic z transform property, it can be written as z to the power I x z also. Now we'll write the DFT formula for the DFT coefficient x1 of z. Sorry, let me write it down. X1 of n is given as this. Xi of n is given as Si of n m k I, where omega m is given as mth root of unity. This basically, this summation of this thing, actually, omega m I, omega m to the power 0, omega m to the power I, up to omega m to the power m minus 1 I corresponds to the kth row of DFT matrix So your xin can be seen as inner product between S0 of n, S1 of n up to S a minus 1 of n and kth row of DFT matrix. Let us denote 1. Let us introduce a new slide, otherwise things won't be clear. Okay, so let us write the equation 1 there again. It is given as xi of n is equal to k runs to 0 to m minus 1 sin wm minus ki. Now take z transform, taking z transform on both sides, you obtain this xi of z is equal to si of z wm ki. Now we use this property that we have mentioned before, si of z. This is not a correct notation, let me correct it. Okay, si of z is z to the power I x of z. Psi of z can be written as k is equal to 0 to minus 1 z to the power I x of z wm minus ki. Now since x z is common, we can take it outside. So k is equal to 0 to m minus 1. It's like zi wm minus ki. If we bring it here, xiz over xz becomes k runs from 0 to m minus 1 z wm to the power minus k all to the power I. This is nothing but the transfer function of the ith branch that we are interested to find, sorry. So if I put I is equal to 0 here, h0 of z is obtained as 1 plus z dot 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 z to the power m minus 1. And suppose we are going to find hk of z, it's 1 plus z to the power let me correct my myself here. We are interested to perform h I of z. It is 1 plus z to the power wm minus 1. Wm to the power minus m minus 1 to the power I. Oh, let me correct myself here. I made error in indexing. It should not be I, it should be not K here, it should be I here. Let me correct it. It should be I here. Sorry for the error. This should be I. Therefore, you obtain h k of z as 1 plus z times wm minus k plus z square wm minus k whole square up to z to the power m minus 1 to m minus k to the power m minus 1. Now if you see here these expressions, these two, compare them, they are basically weighted sum of exponents of z starting from z to the power 0 to z to the power m minus 1, but the weights in case of h naught of z is 1, equal weight, all 1, whereas for hk of z, the transfer function for the kth output branch, the weights are different for different exponent of z. For z exponent of 0, z to the power 0, the weight is 1, but for z to the power 1, the weight is wm to the power minus k. For z to the power 2, the weight is wm to the power minus 2k. So it's a weighted combination. So if you compare them, both 2 and 3, comparing both 2 and 3, can see hk of z is nothing but, if you replace z omega m to the power minus k here, you would get the same expression here if you observe carefully. Therefore the answer should be this one. And let me correct the error here also. It should be k, and it should run from I. Okay. Let us move to our question number 8, which say to, you can see clearly these are input sequences. You are passing through them some upsampler block before this IDFT processing happens. Then you passes through these filters. Then you delay them. Then you add them in a way. So basically what you are doing, you have different input sequences, you are passing through them some upsampler block first, then you are doing IDFT operation, then you passing them through some filtered, then you add them up with a different delayed version of each other. So basically you are combining these input sequences in different manners to synthesize a new sequence. So this is a synthesis filter bank, and that is applicable for both figure 1 and figure 2, because in figure 2, if you see, it performs IDFT operation on different input sequences, then passes them through filter, then passes them through an upsampler block, and at the end add the different delayed version of them to obtain a new sequence. So figure 1 and figure 2 both represent synthesis filter banks, which are correct statement. Now the statement 2 says that figure on right is more efficient than figure on left in implementing synthesis filter banks. We'll see whether the answer is correct or not. Now see on the figure on right, you are perform this upsampling operation after performing all this IDFT and then filtering. After all these operations has been done, then you perform upsampling. Delay is not at all computationally expensive, which you are doing here, just shifting of your sequence, so it doesn't matter at all. But the real computation is happening here in IDFT processing or in passing through this filter, and you are doing the upsampling. What is upsampling? Upsampling basically, as we have seen from previous sessions and lectures, it has been multiple times said that upsampling is nothing but introducing 0 samples between every sample pair of original sequence. But on compared to figure on left, you can see at the beginning you are doing upsampling, and then you are doing this IDFT operation, this filtering, all these computationally expensive processes. So here in the beginning you are introducing additional zeros, and then you kind of wasting your computational resources while performing computation over these zero valued samples. Suppose upsampling by a factor of m, you are introducing additional m minus 1 zeros, and then you perform this IDFT operation. You are spending your computational resources over this additional 0 samples, and then you are performing filtering option also. So the computation entirely becomes a lot more expensive. So this is inefficient way of doing this, because you are introducing zero valued samples and performing IDFT operation and filtering over that, which are computationally expensive process. On the other hand, you are only performing upsampling after all the computationally expensive operations like IDFT or filtering has been done. So this is a efficient way of implementing synthesis filter banks. So the statement is figure on right is more efficient than figure on left in implementing synthesis filter banks. So that statement is correct. So both statement 1 and statement 2 are true. This first option is correct one. Okay, here you can see this system. You first we write it down like this. This H naught of Z, then down sampling, then you pass it through a filter H1 of Z, then again a downsampler block, then filtering H2 of Z, then downsampling by 4 to obtain the output sequence. Now first consider this part first. What it can be written as. You can move it to the left using noble identities. H2 Z square, and this on the right, 2 downsampler block back to back. Now these two filters are placed back to back. We can write their combined transfer function as this: H1 Z H2 Z square. Here both the downsampler block 4 and 2 combines to a single downsampler block of 8. Now here we have this downsampler block again, and at the beginning H naught of Z. Now from this previous example, we are bringing this filter before the downsampling operation, so it becomes H naught of Z H1 of Z square and H2 of Z to the power 4 here. And on the right, this downsampler block with the factor of 2 combines with the downsampler block with the factor of 8, becomes downsampler block of 18. So from this to this, this to this, and you obtain this to this. So you can see that GZ is nothing but H0 of Z H1 of Z square H2 of Z to the power 4. So the option 2 is the correct one. The next question, we encounter this simple problem. What is the value of m in previous equation? So we have already obtained by drawing this, by comparing this and this, we obtain that value of m is going to be 16. So therefore I end this problem solving session here. We will meet on next Tuesday regarding the problems we are going to face in lecture 6. I hope whatever approaches I have shown in this problem that I've solved this session will be helpful for you in solving assignments and of course in the end for exams. So okay, thank you.